Welcome everyone. So today our topic is adjacency matrix, and this is also part of graph theory. Okay. So basically in the adjacency matrix we will see the adjacency relation between the vertices. That means which vertices are adjacent and which are not. So here basically the graph without the parallel edges are considered. Edge is considered for the adjacency matrix, and we will define the adjacency matrix for both the non-directed graph and also for the directed graph. So first for the non-directed graph, and first we start with the connected graph. So here, before going to the definition, first we will just understood the process. So suppose this is one graph, and suppose this is V1 vertex, this is V2, this is V3, and this is V4 vertex. Now you can see that this V1 vertex is actually adjacent to the vertex V4 and V3. Here this V2 vertex is adjacent to the vertex V4 and V3, and in this way. So that's why in like the incident matrix, actually we have taken that E1, E2, E3 in the columns and V1, V2, V3 vertex in the row. So here to calculate the adjacency matrix, we will take the V1, V2, V3 and V4, the vertices in the row and column. In every position we will take the vertices. So column wise we will take the vertices, and also row wise we will take the V1, V2 and V3 and V4. And after that we will put 1 if there is an edge between these two vertices V1 and V1, V1 and V2, and if there is no edge, then we put here 0. So that means here you can see that in between V1 and V1 there is no edge, so we will put 0 because there is no edge in between V1 and V1. So there will be an edge if there is an self loop in this V1. So if we consider one self loop in V1, then there is one edge connecting this V1 and V1, then we put 1. And then V1 to V2, so V1 to V2 there is no direct edge, so that's why we put here 0. Then again V1 to V3 there is one edge, so we put 1, and V1 to V4 there is also one edge, so we put 1. Similarly, from V2 to V1 there is no edge, so there is 0. Then V2 to V2 there is no edge, so this is 0. Then V2 to V3 there is one edge, 1, and V2 to V4 there is also one edge, so we put it 1 here. Then again V3 to V1 you can see there is one edge, this is 1. V3 to V2 there is another edge, so we put 1. V3 to V3 no edge, 0. V3 to V4 there is no edge, so we put 0. Again from V4 to V1 there is one edge, V4 to V2 there is one edge, and V4 to V3 there is no edge, and V4 to V4 also there is no edge. So that's why this is the way of calculating the adjacency matrix of a non-directed graph. So now we are defining the adjacency matrix, and you can see if the total number of vertices is n, like here the total number of vertices is 4, so your matrix would be a 4 cross 4 matrix. So if there are n number of vertices, your matrix will be n cross n matrix, and this is a square matrix. But the incident matrices are not necessarily square, because incident matrix are of the form, if there are n vertices and e edges, it is of the form n cross e. But here you will see that n cross n matrix. So now what is the definition? So for a graph G with n vertices, the adjacency matrix, matrix, it is denoted by AG, is equal to 1 Aij, and which is an n cross n matrix, and is defined as Aij, this value will be 1, this value will be 1 if there is an edge, between Vi and Vj, between these vertices Vi and Vj, and 0 otherwise. So we put 1 if there is an edge between these two, and if we put 0 if there is no edge, and this is for the connected graph. And for the disconnected graph, if we take the disconnected graph property, so first we are taking one example here. So like this, so just construct the adjacency matrix, of the following graph, number 1, just take this, so this is the graph, this is one line, this is another line, so take it as V1, this as V2, this as V3, this as V4, it is V5, there is another line, and it is V6. Okay, so now you can see this is your matrix. So the required adjacency matrix is class niche. So the required adjacency matrix is what? So we take here the V1, V2 in the column and also in the row. We will take the vertices V1, V2, V3, V4, V5 and V6, and here also in the row we will take V1, V2, V3, V4, V5 and V6, and this is the adjacency matrix of the graph G. G is that graph actually. So after that we will just check the connection between them. So that's why this matrix is also named as connection matrix. uh, So because we check the connection between the vertices in by this matrix. So here no loops in the V1, so just in the questions add one loops here, so it will be better. So just add one loop in this V3. So now here V1 there is no self loop, so we put here 0. From V1 to V2 there is one edge, we put 1. From V1 to V3 there is no direct edge, so we put 0, because there is edge from V5 is adjacent to V1 and V2 and V3. So adjacent to V1 there are V2, V5 and V4, not V3. So V4 is adjacent to V1, so we put 1. V1 is not adjacent to V5, so V1 is also adjacent to V5, we put 1 here. Not adjacent to V6, so we put 0. Now if you take V2, V2 is adjacent to V1, so we put 1. V2 is not adjacent to V2, there is no self loop, this is 0. Then V2 is adjacent to V3, so we put 1. V2 not adjacent to V4, we put 0. V2 is adjacent to V5, we put 1, and V2 is not adjacent to V6, so we put 0. Comes to V3, so V3 is not adjacent to V1, V3 is adjacent to V2, V3 is adjacent to V3 because there is one self loop here. Now V3 is adjacent to V4, V3 is adjacent to V5, and also V3 is adjacent to V6. So without this V1, V3 is adjacent to every other vertices. Now V4 is adjacent to V1 and V4 is not adjacent to V2, V4 is adjacent to V3, V4 is not adjacent to V4 because there is no self loop. V4 is not adjacent to V5, so this is 0. V4 is also not adjacent to V6, so we put here 0. Now V5 adjacent to V1, V5 also adjacent to V2, V5 also adjacent to V3. V5 is not adjacent to V4, V5 is adjacent, not adjacent to V5 because there is no self loop. If there is some this type of self loop, then we put 1, otherwise not. And then this V6 is not adjacent to V5, so we put 0. Now V6 is only adjacent to V3, not with V1, not with V2, only adjacent to V3, and not with V4, not with V5, and not with V6. So this is one 6 cross 6 matrix, and this is the adjacency matrix. Now here also you can make some immediate observations from this matrix. So just if you see the row, this row, and you can see that the number of ones in a row actually represent the degree of the vertex. So here this d of the v1, degree of the v1 is 3 1, this is 3. Then degree of v2, this is also 3, and then degree of v3, this is 1 2 3 4 and 5, and you can see it here that 1 2 3 4. And actually for the self loop, the degree of the vertex is more than 1, so that means this you can define this degree concept without the self loop type. But if it is as a self loop, then you can define this type of direct observations. So without that, if the for every other vertices, if there is no self loop, you can define the degrees like this way, that degree of the v4. And what is the degree of v4? This is 1 and 1, this is 2. And then the degree of the v5, so what is the degree of v5? 1 2 and 3 degree of v5. And the degree of v6, so this is equal to number of is 2. So degree of v5 v6 is 1. So this is the process. So if there is no self loop or any parallel edges, so then you can see that in your matrix you can, the number of ones in a row actually define the degree of these vertices. So now we will actually note these observations for the matrix. So if there is no self loop, suppose in your questions if this v3 self loop is not there, so in that case you will not get here this 1, and you will get here 0, and here 1 2 3 and 4. So this is your actually degree of the vertex v3. So this not holds for a degree with the self loop. So now we comes to one of the problem, and where no self loop is considered, and we will see the same thing here, and we will write down some observations. So the graph with for the graph with no self loop and no parallel edges, no parallel edges. So some observations, we are denoting some, noting some observations. So if we take one such type of graph with no self loop and no parallel edges, then actually we will see some of the observations. And the observations are, so let's take another graph here. So like this, we have already taken this type of graph in our previous incident matrix lecture. So this is v1 v2, suppose this is v3, and this is v4. And so there is one parallel edges, so we are not defining this here. So suppose we are taking that, and this is v5. So this is one graph where this is v1 v2 v3 v4 and v5. So now just see it. What is the adjacency matrix? So here the adjacency matrix is adjacency matrix. This, if this graph is denoted by simply G, then the adjacency matrix AG is equal to, so just write down the vertices v1 v2 v3 v4 and v5, and here also this v1, v2, v3, v4 and v5. Now just put the ones and the zeros from the graph. So here you can see v1 there is no self loop, this is 0. v1 to v2 there is one edge, v1 to v3 there is another edge, v1 to v4 no direct edge, v1 to v5 no direct edge, so put here 0. v2 to v1 there is one edge, v2 to v2 no edge, v2 to v3 there is one edge, v2 to v4 no edge, and v2 to v5 there is one edge. Now from the v3 to v1 there is edge, v3 to v2 there is edge, v3 to v3 no edge because there is no self loop, v3 to v4 there is no direct edge, and v3 to v5 there is one direct edge. Now from v4, so v4 to v5, v4 to v1 there is no edge, v4 to v2 there is no edge, v4 to v3 there is no edge, v4 to v4 no self loop, no edge, and v4 to v5 there is one edge. Then v5 to v1 there is no edge, v5 to v2 there is one edge, then v5 to v3 there is one edge, v5 to v4 there is one edge, and v5 to v5 there is no edge. Now just see some of the observations from here in this type of graph. If you can see that every diagonal element is 0 here. So since the graph does not contains any of the self loop, so in the diagonal elements you will get always 0. And also if you see the graph, you can see this graph is actually symmetric graph. So this is 0 1 1 0 0 and this is 0 1 0 0. So if you just track the pattern, and you can see that this is just nothing, this is one of the symmetric matrix. So for the non-directed graph of this type with no self loop and no parallel edges, so you will see that your matrix, adjacency matrix, is a symmetric matrix. And also the sum of ones, number of ones actually represent the degree in this uh, degree of the vertices. So here d of v1 this is equal to 2, here the degree of v2 this is equal to 3, and degree of v3 this is also equal to 3, degree of v4 from here this is equal to 1, and degree of v5 this is equal to 3. So you can directly read out the degree from the matrix. So now we are noting actually these observations for a graph with self loop and no parallel edges. So number one, the entries along the entries the entries along the principal diagonal of A, the principal diagonal of A are all 0, are all 0. Okay. And then we comes to the second part, number 2, and where the definitions of the adjacency matrix actually don't work for the uh, don't actually provisions for the parallel edges, because there is a connection between v1 and v2 if by any one edges, so then we don't require any other edges. So next, another thing, so degree of vi, degree of vi, and that is the d of vi is the number of ones, is the number of ones, number of one in the ith row or ith column, in the ith row or the ith column, or the ith column always. And you can also do it in this way, that if you take the product of these two matrix, if you take the product of these two matrix, then at the diagonal you will actually get some values. So this is actually, this represent also the degree of this vi. So that means suppose an adjacent matrix is given in this way, that some 1 1, suppose if we take simply two vertices problem, and these are suppose 1 1 and 0 0, this type of, that means this type of matrix, suppose V1 and V2. So if you see here that the this is V1, this is V2, and this is V1 and this is V2. So because there is no V1 V1 no connection, this is 0. So V1 to V2 there is connection 1, and V2 to V2 there is connection 1, and then V1 to V2 there is no connection. So V2 V2 there is no connection, so this is 0. So this matrix is your A. Now if you calculate the A square of this matrix, you will get 0 1 1 0, and here also 0 1 and 1 0. After that, just take the product of these two matrices and you will get 1, and after that you will get 0 1 and 1 0. This is 0 and this is 0 and this is 1. Now this value in the main diagonal actually represent the degree of the each vertices also. So this is the d of v1, the diagonal value at the diagonal entries, and this is d of v2 value at the diagonal entries. So that means if this is your A, so if you product it or if you calculate the A square value of this matrix, and then also the diagonal entries actually represent the degree of the vertices, but it is very laborious to calculate, so that's why counting along the diagonals, counting along the rows of the columns would be better. So this is just one of the property of this type of non-directed graph, so that's why we will write down that here. So just write it here. So number 3, and the degree of the VI, d of VI, is the ith entry, on the main diagonal, of this matrix square, where A is the adjacency matrix. And number 4, so for a non-directed graph, and the adjacency matrix is without non-directed graph, without self loop. Without that, we already write down at the heading because we are observing all these properties for this type of matrix, but we are writing it again. So without self loop and parallel edges, the adjacency matrix is symmetric. So for the directed graph, it is not necessary that the adjacency matrix would be a symmetric matrix, and you will see that for a directed matrix it is not necessary. So that is the observation from the adjacency matrix. Now we will define the same adjacency matrix for the disconnected graph. So for the disconnected graph, we all know that there will be some connected components. For the disconnected graph, now take this. For the disconnected graph, and so for two components G1 G2, so let G1 and G2 be two connected components, components of a disconnected graph, G. Okay. Then the adjacency matrix of that G is denoted by AG, and defined as this AG would be equal to A of G1 0 0, A of G2. So where these zeros are the null matrices, these zeros are the null matrices here, and this AG1 and AG1 and this AG2 are adjacency matrix of the components G1 and G2, of the components G1 and G2. That means we will calculate, since G1 and G2 are connected, so by using the previous method you can easily calculate the adjacency matrix for that G1 and for that G2. So after calculating this AG1 and AG2, so what you have to do, just assemble these matrices to form the disconnected graph. So now we will take one example from that. Okay, so let's take this problem. So construct the adjacency matrix. Construct the adjacency matrix for the graph. Suppose this is the graph, and this is another graph connecting this. So this is V1, V2, V3, this is V4, and this is V5, V6, V7, V8, and V9. Now you can see that this graph is actually disconnected graph. So this is the G graph. You can see easily that this G graph is a disconnected graph. That means, but these are two connected components. These are two connected components. So this is one component and this is another component. So that means this is G1 and this is G2. So just what you have to do, you have to calculate the AG1 and AG2, and after that your G will be formed like this, that just place this AG1 and AG2 diagonal wise and fill the other values with 0. So this will be your adjacency matrix for the given matrix G. So the required, we will actually directly construct this matrix using all the vertices. So here the required adjacency matrix is required adjacency matrix is, so we start with the values. Suppose and in the column wise we will write down all the vertices v1, v2, v3, v4, v5, v6, v7, v8, and v9. And also in the row wise we have to write down all these v1, v2, v3, v4, v5, v6, v7, and also v8 and v9. So this one, right? Also v7, and then v8 and v9. After that, just calculate the matrix. So here the first graph actually contains from v1 to v5. So we are just marking one separator line here. So that means this will be the first square matrix, and after that we will calculate the second matrix, and these all values will be zero matrix. This is also a zero matrix, and this zero matrix is a zero matrix of 5 cross 5, 5 cross 4, and this zero matrix is a 4 cross 5 matrix. And here you will get one 4 cross 4 matrix, and here one 5 cross 5 matrix, and overall your matrix is a 9 cross 9 matrix. Now just take the relation between these. So v1 there is no self loop, so put here 0. v1 v2 1, then v1 to v3 there is no connection, so put here 0. v1 to v4 no connection, and v1 to v5 no connection because it's a pendant vertex. Then from v2 to there are four adjacent vertexes from the v2. So v2 to v1, v2 to v2 there is no connection because there is no self loop. v2 to v3, v2 to v4, and v2 to v5 there are They all are actually adjacent to the V2. Then V3 to V1 there is no connection. V3 to V2 there is one. V3 to V4 no connection. V3 to V5, V4 no connection. V3 to V3 and V3 to V4 both there is no connection. And V3 to V5 there is connection. Put here one. V4 there is no self loop, and also V4 to V1 no direct connection. Put here 0. V4 to V2 1. V4 to V3 no direct connection. V4 to V4 no self loop. V4 to V5 it is 1. Then V5, so V5 to V1 no direct connection. V5 to V2 there is one connection, so V5 to V2 this is 1. V5 to V3 this is 1. V5 to V4 this is 1, and V5 to V5 since there is no, so put here 0. So these are the first, this is the first adjacency matrix for the component G1, and you can just check that this is also symmetric matrix. So after that, do it for the G2. For the G2 there is V6. So we start with V6. So V6 to V6 there is no self loop, put here 0. V6 to V7 there is no connection, so put here 0. V6 to V8 there is connection, and V6 to V9 there is no connection, so put it 0. Then from V7, so V7 to V6 there is no connection. V7 to V8, V7 there is no self loop. V7 to V8 there is one connection. V7 to V9 there is one connection. Then V8, so V8 to V6 there is one connection. V8 to V7 there is one connection. V8 to V8 no self loop, and V8 to V9 there is no connection. Then V9 also one pendant vertex. So V9 to V6 there is no connection. V9 to V7 there is one connection. V9 to V8 no connection. V9 to V9 no self loop. And then these are just 0. You can also fill like this 0 0 0 0, and also you can write down this 0 or null matrix with proper dimension. So this is the required adjacency matrix. So this is the portion. So where from the adjacency matrix you have calculated the, from the graph you have calculated the adjacency matrix. Now in the next problem we will see that how to draw the graph from the adjacency matrix. So let the graph adjacency matrix is given, and you have to find the graph from that, and just take one of these type of problem. So the question is, this is the question. So draw the graph corresponding to the following, corresponding to the following adjacency matrix, following adjacency matrix. And this is the graph, suppose 0 1 0 1 0. Then this is 1 0 0 1 0 1 0 1, and this is 0 1 0 1 1. This is 1 0 1 0 0, and this is 0 1 1 0 and 0. Okay. Now first what you have to do to draw the matrix. So first mark these vertices like this. As we all know that V1, V2, this is V3, this is V4, and this is V5, and there also this is V1, so V2, V3, and V4 and V5. Now to draw the matrix, what we have to do? So consider any row. Suppose consider the row corresponding to V1, then also consider the column corresponding to the V1. So whenever you actually consider this row, you have to consider this column, and after that join the vertices. Just observe which vertices are adjacent, and then join those vertices. And similarly do it for the other. So whenever you take V2 row, you will take the V2 column, and then again find the connections between the vertices and join them suitably. So this is the process. So now we will start to join that. So first of all, see, you can see that this is one of the symmetric matrix. This is one symmetric matrix. These are symmetric pattern. This pattern is a symmetric pattern. So that's why you will get one of the undirected graph here. Probably there is an undirected graph, and now we starting by the undirected graph. So first we take the V1 and the V1. So the V1 row, this V1 row and this V1 column, and if you take these two, then what you will see that V1 is adjacent to V2 and V1 is adjacent to what? V4. And here also the same thing, actually V1 is adjacent to V2 and V1 is adjacent to V4. So just take the V1 here. So I am taking the V1 here. Suppose this is the vertex V1, and you can see that V1 is adjacent to the vertex V2 and also V1 is adjacent to the vertex V4. So we have taken that these two are adjacent vertex. Now from the V1 go to any of these vertex row, any of these vertex row. So now we are going to the V2 vertex. Now we see the relationship in the V2. So just again take the V2 row. So this is the V2 row and this is the V2 column. Now just see it. So V2 is adjacent to V1, V3 and V5. So here also V2 is adjacent to V1, V3 and V5. So this V2 is adjacent to V1, it is already over. Then V2 is adjacent to V3 and V5. So again take these two adjacency, that V2 is adjacent to one V3 and one V5. Take this V3 and take this as V5. So V2 is adjacent to V3 and V5, and also V1 it is already done. So V2 is adjacent to V1, V3 and V5. Now again we move to the any other of the vertices. So just move to the V3 and check it. So the V3 row is that, and corresponding to V3 column is that. So just check it. So V3 is adjacent to V2 and V4 and V5. So V3 is adjacent to V2, it is already over. Then V3 is adjacent to V4. So V3 is adjacent to V4 means connect those, and V3 is adjacent to V5, so connect this also. So V3 is adjacent to V2, V4 and V5, it is over. Now go to V4. So now we are going to V4, and from the V4 just again do the same thing. So this is the corresponding V4 row and this is the corresponding V4 column. So V4 is adjacent to V1 and adjacent to V3. So V4 is adjacent to V1 and V3, it is already over, so we don't have to do anything now. And then similarly for the V5, if you go to the V5, so this is the V5 row and this is the V5 column. So here V5 is adjacent to V2 and V5 is adjacent to V3. V5 is adjacent to V2 and V3. So it is also verified. So that means this is the non-directed graph. So this is the required graph. Okay. So from the given adjacency matrix. So that means if a matrix is given, you can also draw the graph from the matrices. So if the matrix is given, you can draw the graph, and also if the graph is given, so you can draw the matrix. So just take one or two problems to find the adjacency matrix as homework. Take one problem. So number one, construct the adjacency matrix. Construct the adjacency matrix for the following graph. For the following graph, and the graph is that. So this is the graph. Stick it here, and this is that. And after that, take one of the self loop here, and now you can see that this is V1. Take it as a V1. This is V2. This is V3, V4. Okay, take it as V3. Take it as V5. Take it as a V4, and it as V6. So construct the adjacency matrix and for the following graph, and then number two, construct the graph from the adjacency matrix and The adjacency matrix is like that. So 1 0 0 and 1 0 and 0 0, okay, 1 0. This is 1 1 0 1 1 1 0 1. This is 0 1 0. This is 0 1 0. This is 0 0 0 and 1. So this is the matrix AG, and you have to construct the graph and form this adjacency matrix. So these two are the homework just for the practice. Okay. So that's the end of the non-directed graph, the adjacency matrix for the non-directed graph. And our next topic will be the adjacency matrix for the directed type of graph. Okay, so our new subtopic is the adjacency matrix. Adjacency matrix for the digraph or the directed graph. So here also we define it for the connected and for the disconnected graph. So for the connected graph, so for a graph G, for a digraph, G with n vertices, the adjacency matrix this AG is equal to Aij, and which is n cross n, is defined as Aij, this value will be 1 if there is an edge directed from Vi to Vj. So if there is a directed edge from Vi to Vj, then we put 1. But if the direction is from Vj to Vi, so then we will put 0 here, because this is one of the directed graph. But for the undirected graph, if there is an edge between Vi and Vj, then we put for every pair, so that means from Vi to Vj or for Vj to Vi, we put 1. But for the directed graph, we only put 1 if it is from Vi to Vj. But if it is from Vj to Vi, then we put 0. So 0 otherwise. And for the disconnected graph, if it is disconnected graph, and if G1 and G2 are connected components, if G1 and G2 are connected components of the disconnected digraph, of the disconnected graph G, then the incidence, not incidence, in the adjacency matrix for the graph G, is defined as AG. This is equal to the matrix, just place the adjacency matrix for the AG1 and AG2, and then here 0 and 0. So this is one n cross n matrix. The n is the total number of vertices of the matrix of the graph G. So this is the AG, and where you all know that this AG1 and AG2, these are adjacency matrix of the components G1 and G2 respectively. G2 respectively. So first we will calculate the adjacency matrix for both these G1 and G2 and using this rule. After that we assemble these two matrices diagonally just to produce the adjacency matrix for the disconnected graph G. So this is the method and it is like the previous same method. So just take one or two example to understand the process. So first of all, this is construct the adjacency matrix. Construct the adjacency matrix for the following diagraph. And what is the diagraph? This is the figure. Okay, we need some space for the matrix, so that's why this is suppose the diagraph. There is one self loop in this direction. So this is V1, this is suppose V2 and V3, it is V4 and the direction are like this. Suppose the direction is in this direction. So this is the graph and you have to calculate the diagram for the adjacency matrix. Now we will start with the required adjacency matrix. Required adjacency matrix is denoted by AG and this AG is just the matrix. Just place the vertices here V1, V2, V3, V4 and V5. Now place here also the same vertices V1, V2, V3, V4 and V5. So after that just we will found the relation. So this is a directed graph. So and there is one self loop from V1 to V1. So we put 1 here. Then V1 to V2 there is one directed line V1 to V2. So that's why we put 1. Then V1 to V3 also there is one directed line. So we put 1. So from V1 to V5 and I think we don't have V5. So why we are taking this V5? We don't need this V5 na. So this is V4 and so then from this V1 to V4 there is no directed line or direct line also. So that's why we take it 0. Then V2. So V2 to V1 there is no directed line because the direction is from V1 to V2. But V2 to V1 there is no direct line, so we put here 0. From V2 to V3 also there is no V2 to V2 there is no loop, so we put 0. V2 to V3 there is no directed line. Okay, direction is in the opposite side, so here we also put 0. And V2 to V4 obviously there is no direct connection, so here also we put 0. Now comes to the V3. So if you check the V3 pattern, what you will see? What is the case for the V3? So for the V3, so from V3 to V1 there is no directed line, so we put here 0. From V3 to V2 there is one directed line, so we put 1. From V3 to V3 there is no self loop, so we put 0. V3 to V4 there is one direct line, so we put 1. Then V4 to V1 no directed line, 0. V4 to V2 no line, 0. V4 to V3 no directed line, 0. And V4 to V4 also there is no self loop, so that's why we also put 0 here. Okay, so this is the adjacency matrix for the first problem, and you can see that this matrix is not symmetric matrix. So this is not a symmetric matrix. Not a symmetric matrix. So we can just state that for a non-directed graph, for the digraph, actually for the non-directed graph it is symmetric, but for a digraph the adjacency matrix is not necessarily symmetric. Is not necessarily symmetric. So that means if the problem is given in this way, that from the matrix generate the graph, then first you can observe that is it symmetric or not symmetric. If it is not symmetric, then obviously you will get some directed graph here, and you have to draw one directed graph, but not the non-directed type of graph. Like the previous problem is with the symmetric matrix, so that's why we draw a non-directed graph. But if you get this type of matrix, then obviously the graph generated will be a directed graph. So now we will take another problem, and which is of a disconnected graph. So installment, we are taking another problem and with a disconnected graph. So just take this. Question. So here construct the adjacency matrix. The adjacency matrix of the following graph. Okay, so from where we start first? This is the graph, and suppose this direction in this way, this direction in this way, this is the direction, and we are taking another edges in this direction. Okay, you can see these two are not parallel edges because the direction is different now. So this is another, and another form, suppose this is another disconnected form, and with this type of direction. Now just defining this is v1, v2, this is v3, v4, and there is v5, v6, and v7. So this is the graph, and this is G graph actually, and in this G you can see that there are two components. This component is G1 and this component is G2. So this is the first component, this is the second component of the disconnected graph. Now to calculate the adjacency matrix of this graph, first what you have to do, you have to draw some vertices line, and like this. So suppose your required matrix is A of G, and this is equal to some rows and columns will be there. Those are V1, V2, V3, V4, V5, V6, and V7. And here also V1, V2, V3, V4, V5, V6, and V7. Now we are drawing the separator line and with this pattern. So these are actually from V4 to V4, and another square matrix will be here. And here you will get 0 of 4 cross 3. Here we will get null matrix of 3 cross 4. Okay. And we have to fill these two blank boxes with the adjacency matrix of this directed graph. So let's start putting 1 and 0. So for V1 and V1, you can see there is no self loop, so put 0 here. From V1 to V2, there is one directed line. This is the directed line, so that's why we put 1. From V1 to V3, there is one directed line, we put 1. From V1 to V4, there is no directed line because the direction is towards V1. So V1 to V4, there is no, so that's why we put 0. Then comes to V2. So V2 to V1, this is the line. So V2 to V1, we put 1. V2 to V2, no self loop, so we put 0. V2 to V3, there is one line, this is the line. So V2 to V3, we put 1, and V2 to V4, this is the line. So V2 to V4, we also put 1. V3. So V3 to V1, direction is opposite. So V3 to V1, this is 0. V3 to V2, also the direction is opposite, we put 0. V3 to V4, actually it is out from the V3 and go to the V4, so that's why we put 1. V3, no, V3 to V3, this is no self loop, this is 0. And V3 to V4, it is 1. Then comes to V4. So V4 to V1, it is going. So V4 to V1, this is 1. V4 to V2, it is in the opposite direction. So V4 to V2, it is 0. V4 to V3, it is also in the opposite direction. And that means this is also 0. And V4 to V4, there is no self loop. So that's why it is also 0. So this is the end of the adjacency matrix of G1. Then for the G2, actually V5 to V5 no self loop 0. V5 to V6 there is no directed graph, that's why this is also 0. And V5 to V7 no connection, so it is 0. Then V6 to V6 to V5 there is one road, so V6 to V5 it is 1. V6 to V6 no self loop 0. V6 to V7 directed line 1. Then V7 to V5 there is no directed line 0. V7 to V6 the direction is opposite, so that's why we put 0 here. And V7 to V7 no self loop, this is also 0. So this is the adjacency matrix of the disconnected graph. Okay, so that is the process how you can directly calculate the adjacency matrix of this type of directed graph. Now we comes to another problem where the adjacency matrix will be given and you have to calculate the graph, but this time we will give one of the asymmetric, that means not a symmetric matrix. So that's why take one matrix and construct the graph. So construct the graph from the, this is the problem, construct the graph from the adjacency matrix AG is equal to, this is the matrix, take it, so 0 0 0 0 1, then 0 0 1 0 0, then 1 0 0 0 and 0, then 0 0 1 0 and 0, and then 0 1 0 0 and 0. So this is the adjacency matrix and you have to draw the graph from this. So that's why we have already explained that what we have to do, we have to take any one of the vertices. So first of all we have to mark the vertices. So this is v1, v2, v3, v4 and v5. So here also the same thing, v1, v2, v3, v4 and v5. So after that we have to take any one vertex to start and take the corresponding row and the columns. So if you start with v1, take the corresponding row of v1 and also the column corresponding to the v1. Now so the relationship, now you can see that v1 is adjacent to v5 and also v1 is adjacent to v3 and v5 here. So here adjacent to v3. So from the row v1 is adjacent to v5 and from the column v1 is adjacent to v3. But if you see the relation here, that v1 v3 there is 1, v1 v3 there is 1, but v5 v1, v5 v1, if you take that v5 v1, these elements actually it is 0. Okay, so v5 v1 it is 0. That means there is one edge between that, but the direction is from v1 to actually not v1 v5, take it. So v1 v5 this is 1, but the v5 v1 there is 0. So the direction is from v1 to v5. So if we start from the v1, so suppose this is our v1, so we will take one directed line from v1 to v5. So that's why from v1 to v5 you will get 1, but from v5 to v1 you will get 0. Now if you take the column, then you can see again the same thing, that v3 v1 there is 1, this is this one, that v3 v1 there is 1, but if you take the v1 v3, this term you can see this is 0. So v1 v3, this term is 0. So that's why there is another line connecting the V1 and V3. First we draw the connecting line. So suppose this is the V1 and V3. Okay, we are you can connect this also in this way. So these are V1 and V3. But the direction is from V3 to V1, not from V1 to V3. So direction is from V3 to V1. This is the direction. So that's why in V3 to V1 you have 1, but from V1 to V3 you have 0. And that's the over of the first vertex, first row and first column. Okay, after this, just go to any of these two vertex, any of this, either V3 or V5. So if you go to V3, so just if we go to V3 and if we mark the corresponding rows or columns, so V3 rows and V3 columns, you can see that V3 is adjacent to V1 by the row. V3 is adjacent to V1 and it is already over. V3 is adjacent to V1 from V3 to V1. Now comes to the column. So if you comes to the column, you can see that V2 is as adjacent to V3. So corresponding to V2, V3, you have 1, and corresponding to V4, V3, you have 1. But for the both, if you see that V3, V1, the opposite V3, V2, corresponding to, that means from the row, if it is V3, V2, then it will be what? 0. And if you take the V3, V4, this is also 0. So V3, V2 and V3, V4 both 0. But from the column, their V2, V3 and the V4, V3 both are 1. That means again there is a connection between the V3 and V2, V4. So just connect again. So V3, from the V3 there are two adjacent side, one is V2, another is V4. So take here V2 and take here V4, and the direction is from V2 to V3. So just take the direction from V2 to V3, and here from V4 to V3. So this is the direction. So now V3 is also over. So we have already covered V1 and V3. So at the next stage, we will take any of the other vertices. So let's take the V2. We are taking V2 now. So now take the rows of V2 and take the columns of V2. Now, if you first check the row, then you can see that, so okay, we are taking that V3, V2 is equal to 0, and here also V3, V4 is equal to 0, just to complete. So this is the observation corresponding to V2, and these are the observation corresponding to the V1, this is the observation. And now if you observe the no, this is not V2, this is V3, and V2 case, if you observe the V2 case, so what are the observation? So from the V2, first we take the row. From the row, there is a connection from V2 to V3. So V2 to V3, this is 1. And if you take the columns, you can see that V5 to V2 there is 1. V5 to V2 there is 1. That means every other value is 0. So from the V2 there is two connection, V2 to V3 and V2 to V5. So V2 to V3 it is already there, it is verified, and the direction is from V2 to V3. Now V2 to V5, so we have to join these two. So just join V2 and V5, and the direction is from V5 to V2. So this is the direction from V5 to V2. So it is over of the V2 case. So now we comes to the V4 case. Now for the V4, so for the V2 this is the observation. Now comes to the V4 case. So if you take the V4 and this is the row and this is the column corresponding to V2, and if you observe in the column there is nothing, but from the row there is one V4 to V3. So corresponding to V4, V3 there is 1 and every others are 0. So just take it V4 to V3. So that means V3 is connected to V4, it is already connected, and the direction is from V4 to V3. So it is already done and it is all now verified. So it is also okay. So V4 is completed. So after that we comes to the V5. So first one or two rows will be difficult to understood, but after that you will see that most of the edges are already uh, drawn, and then just you have to verify that. So if you now take the V5, so this is the V5 column. So in the V5 column you can see that one, if you from the take the row wise for the V5 connection, if you take it row wise, so there is a connection from V5 to what? V2. So V5 V2 V5 V2 this is 1, and the row wise V1 V5 is 1. So here, so V5 V2 is 1, and the next thing from the column wise V1 V5 is 1. So just take it V1 V5. So V1 V5 this is 1. Now see it. So V1 V5 is already over. This is the V1 V5, and V5 V2, and this is already over V5 V2. So we have taken both. So this is a required graph. So the required graph is that. So that's the way of drawing a directed graph from an adjacency matrix. Okay. So now take one or two homework just for the practice, self work. Now just write down this. So first, calculate the adjacency matrix of the following graph. So calculate the adjacency matrix of the graph. So this is the first graph, number 1. Take it and then this way. For that, take one or two edges here, and just we are drawing one self loop here and one self loop here. Now I'm giving the direction. Here is the direction. There is another direction. This direction are opposite, so these are not self loops, they are not parallel edges. And here also the direction is this, and here the direction is this one. So after that, this is V1, this is V2, and take it as in this way. This is V3, and then V4. Take it as V3, this as V4. So calculate the adjacency matrix for this detected graph. And number 2, so take it like this. So now just draw this two edge, and here also the same thing, and here two of the vertices are given like this. So this is one of the graph, but and here this one disconnected graph. You can see it V1 V2, connection between V3, this is V4, this is V5, V6, and V7. Just calculate the adjacency matrix of that graph. Okay, so this is the graph. I think every edge have some directions. Now calculate the adjacency matrix and for the following graphs. And if you want to draw one incidence adjacency matrix, one graph from the adjacency matrix, so then take it. So construct and graph from the adjacency matrix from the adjacency matrix. That means you have to draw one graph, and from the given adjacency matrix. So just take one adjacency matrix and then draw the graph. What do you think? So just take one problem. So take this 1 1 1 0, and then 0 0 0 and 1 and 0, and then 0 1 0 1 and 0 0 0 and 0. So take this problem, and you can see this is not a symmetric matrix, so that means whatever you get, it will be a directed graph. So just do it. Okay, so that's the end of this lecture. So thank you all for watching.